go ahead?
Yes.
Okay, I guess they were faster than I thought, but he's ready to start. So I'd like to introduce Eric Matsen. We'll be talking about phylogenetic geometry today, it looks like.
Yeah, so I changed. Oh, oops. That was completely off the record.
But you had it on.
Started good.
Yes. Okay, now we're going to start right on time. So Eric Matsen will be talking today on phylogenetic geometry.
Okay, yeah, so I did change a little bit. As we're talking about challenges and whatnot, I really think that this is something that's been around forever. I mean, since the very beginning, and it's still something that's really challenging and something that I think we should be thinking more about. So I'd just like to make a quick metaphor. So imagine we have a planet, and there's a satellite that is going around this planet. And we know that the satellite is somewhere on this, on this orbital track, and it's sending us signals. And we're able to locate the satellite based on the signals, but it has some error. And so say we have, we get a signal, and we think it's about here. So that's where we locate the signal from, but maybe there's some kind of normally distributed error or something like that. We'd like to figure out where the satellite is. So, if we do maximum likelihood in this case, we're just going to kind of project down, and we think, okay, well, the satellite's right about there. Well, let's say we've got two satellites. So we've got a satellite here and a satellite here, and we get a signal. We don't know which of these satellites the signal is from. And we want to figure this out. So we can do this. This isn't actually very hard at all. And that's because we understand the geometry. Well, of course, this is just a metaphor for phylogenetics, especially likelihood phylogenetics in particular. But the point is we don't know what the geometry is. So that's the real difficult part. But I mean, just to go through it, so we have some phylogenetic data here. I'll be explaining this in just a second. And each one of these corresponds to some topology. So that's really what the metaphor is about. So before I kind of go on to anything else, I want to talk about what is the data that we use. And this is the data that's used in majority of, well, basically all phylogenetic methods. It's these site pattern frequency vectors. So I'm just going to be calling them a data vector because site pattern frequency vector is too long. And basically, a site pattern is simply an assignment of states to the taxa. And then the probability is just the probability of seeing that. So if you're looking at alignment, it's if you pick a random site, what is the probability of seeing that pattern in the alignment? And if it's coming from a tree, kind of simulated data, you just simulate data down the tree, you get this. So again, I'll be calling those data vectors. Okay, so instead of having these satellites going around this planet, this is what we really actually have. I mean, this is a cartoon, of course, but we have this probability simplex, and then instead of these loops, we have these subvarieties. So that's just what I'll be calling them. I won't be explaining why. But we have these subvarieties that represent each model topology. And although there's a cartoon, there's some elements of truth. For instance, there is some symmetry here. So of course, if we change A, let's see, what do? We change B and C. We get from this one to this one. We do the same thing with data, and the whole thing just kind of flips around. So we have three of them. But there's one part of this I'd really like to emphasize, which is it's mostly empty space. So most of the time when we get a data vector, it's not going to be sitting on one of these varieties. And so the classical identifiability results, which are really important and really good, however, only really tell us typically about what's going on. If you start here, you generate some data, and then it takes you back onto the subvariety. So you're showing that essentially if you generate data that you know is a tree, then you fit it on the tree, then you get what you were supposed to get. But most of the time, we're going to be sitting somewhere out here, or who knows where. So and this gets worse as the number of attacks that grow up. I mean, so the dimension of the space for the two-state model is going to be 2 to the n minus 1 minus 1. But these are just going to be running linearly. So you have exponential kind of ambient space just linear growth of these sub-variety dimensions. So we can look at some actual projections. This is, I couldn't quite fit this on, but a really nice article by Vigneault and Kim talking about this geometry. And you can stare at this. I still am really not able to make heads or tails of what's really going on here, but this is kind of an actual projection. We can look at this, but I think we really need to be proving theorems about the geometry. So here are some theorems. So this is just a selection. There's much more than this, but from the likelihood perspective, there's some really nice work by Shore et al. Talking about multiple maxima of the likelihood function, and then the algebraic geometry has pretty much, I mean, from an ideal theoretic perspective, has been pretty much wrapped up by Sternfels and Sullivan. And there's also some work about how they fit together, so in a combinatorial and topological setting. But we really need to kind of combine these settings. We need to understand how do they fit together, not in a combinatorial sense, but in a geometric sense. And this is really kind of just getting going. I mean, there's of course the really nice work of Allman and Rhodes, Stefankovic and Goda, also Steele and the man on the camel. Zikli. Thanks. And I mean, so, but we really are just kind of starting to get an understanding of what's going on here. So this is kind of what I like to talk about. So are we in a setting that's like this, where we can kind of pretty easily divide things up so that if you get a point up here, then we're going to end up on one of these sub-varieties. We can kind of partition the space up nicely, or do they kind of just wrap around on each other? So this is a kind of a vague question, but you'll see the way I want to be defining it. And I want to define it using convex hulls. So a convex hull is just all the possible averages of the points that you start with. So if we start with a point here and a point here, so just 2 points, the convex hull, this is just this line, and that's all the weighted averages that we can get between the 2 points. Same thing here, we have 3 points. Well, we just take all the possible weighted averages, or we can take the convex hull of the line. And you can think of the convex hull as we just take a big rubber band, and we put it around the space, and then we kind of let it shrink down as much as it can, and that's your convex hull. And that represents the fact that the convex hull is the smallest convex set that contains all of your points. So, okay, so now we can kind of rephrase our question. So what do the convex hulls look like? So do they kind of, sit like this, kind of only intersecting at a small amount of points, or do we have something like this, where we have quite a lot of intersection between the convex hulls? And in particular, do the convex hulls intersect other subvarieties? So if we take the convex hull, we take kind of the average, essentially, of data vectors coming from one tree and another tree of the same topology, is it possible to get a tree of a different topology? And so this isn't just kind of a theoretical geometric question, it's also kind of a practical question. I mean, people have been talking about these mixture models, and very nicely, Matteo kind of introduced this example for me already, but you have, some sites that are on stems and some that are on loops, and those evolve in different ways, most certainly. And instead of just thinking about a single process explaining the data, we're probably going to be in a situation more like this, where we have some of the sites are evolving in a tree that might look like this, some in a tree that might look like this. Each of these generating data, we take a weighted average of these data vectors and we get a mixture. So again, these mixture models are being used much increasingly as time goes on, so that we need to understand their geometry. And they're very difficult for phylogenetic inference. And this is just one of the papers describing it. It's probably the one that got the most coverage. So what happens is we take a tree that looks like this. So hopefully you can see this. This is a tree of topology A and B together, and C and D together. And then we take a tree of this the same topology again, but different sets of branch lengths. We take a mixture. And maximum likelihood Bayesian methods and maximum parsimony all give you the wrong tree. And it's so Mike and I kind of wondered what's going on here. So is it possible that a mixture like this would actually give us a data vector that looks quite a lot like a tree of a different topology? So we use the Hadamard transform, which is an invertible transformation between data vectors and their trees in a simple model. And phylogenetic invariants, which are quite a very nice tool. And they answer answer the question, if we have a data vector, is it possible this data vector came from a tree of a given topology? It's quite a nice system, a bit more complicated than I'm really telling you. And we assume the binary symmetric model. So equal probability of transitioning between two states. So this is sort of a toy model, but it does allow you to kind of get an idea of what's going on in the phylogenetic setting. It's, we'd like to extend these results to something other than the binary symmetric model. And we came up with these examples. So this is quite strange. So we take a vector, we take a tree with one set of edge lengths and then a tree of another set of edge lengths with the same topology. We take their data vectors and take a weighted average of these data vectors, and you get a tree of a different topology. So that's really sincerely quite bizarre. And this is actual data. This isn't just model. This isn't just inference. It's not that maximum likelihood or parsimony or any method. It's just that this tree fits exactly what's going on with these mixture vectors. So that is weird. Here's another example. And we don't just have a sort of mixed bag of examples. You can parameterize exactly when these things happen. And it's a I'm not going to go through this in detail, but suffice it to say that there's a 9-dimensional space of examples in the 11-dimensional parameter space. So 11 dimensions comes from 5 branch lengths from one tree, 5 from another tree, and 1 mixing parameter. So here's a geometric view of what's going on. This is an actual projection of these subvarieties. So it may not make too much sense just by looking at it, but since we have sort of this gray thing is going like this, and then this black sheet is coming down like this, and then we're taking an average, and so we're taking a line between 2 points of the gray sheet, and then that's intersecting the black sheet. So the black sheet you can't see very well, but it's kind of coming down, so it's projected out of it. And you can see that because this straight line intersects the black sheet, then you get a tree of a different topology. And you can see even just from this projection, there's going to be a 4-dimensional set because we can kind of turn this one around, turn that one around, and it seems like it'll stay on that subvariety. Okay, so yes, so convex holes do intersect other subvarieties. So I think that's a fairly interesting fact. But the question is, how much do they cross over? So we have this, we know now that we have this example, this thing happening. We get this subvariety sitting inside the convex hole of this other one. But how big is this green area? So I wanted to say, so I'm calling this green area the non-identifiable region. So it's the intersection of this convex hole, so this guy here, and this convex hole here. So why am I calling this the non-identifiable region? I'm calling that because these data vectors, if you're given a data vector like this, it can be represented as a mixture of this type or a mixture of this type. So a mixture on this topology or this topology. So if we're given such a data vector, we don't know, did it come from this topology or this topology? So it's non-identifiable. Okay, so it turns out it looks like this. So first of all, so these curvy things have to become sort of boxy things. Well, the reason for that is because it turns out that these convex holes are polytopes. So what is a polytope? It's just you take some space and you cut it down with high-dimensional knives, a finite number of them, and you get this kind of blocky shape. So you can see actually without too much difficulty that these are polytopes. And once you know that, then it's really quite easy because the intersection of a polytope is a polytope, and it's easy to kind of understand what the boundaries of these polytopes are. And we found out that if you take, let's say we take this convex hole here to be 100%, then this non-identifiable region, which is the union of the purple and the green, is about 57% of this big guy. And then this purple guy is about 47%. So I might have not gotten the volumes quite right. I mean, this was just freehand. These are 7-dimensional polytopes, so it's difficult to draw them. But suffice it to say that there's quite a lot of non-identifiable vectors. And what's really weird is this purple region is triply non-identifiable. So any point in this guy can be expressed as a mixture on any of the 3, 4, these aren't, I mean, yeah, so this deserves more investigation, and you know, one of my next projects will be to understand this in a group-based formulation. So for some other four-state models, So this is another interesting point, I think, and it's actually quite a simple argument. But we've been thinking about genericity, and these previous examples, not this one, but this one's essentially a non-generic result because there's a 9-dimensional set of examples in the 11-dimensional parameter space. So that means that usually you won't run into these. However, there is this. You can see that ML will often will kind of generically in certain regions choose the wrong tree. So this is how this works. So if we take one of these nasty examples where we have a mixture of 2 branch lengths on one topology making a tree of a different topology, what that means is that mixture is sitting right on this subvariety of this topology. So of course, just by continuity, if we perturb in any direction, if we perturb just a small amount, the maximum likelihood will go back to a point on this same topology. And in particular, we can kind of move these edge lengths in the mixing parameter around a small amount, but in any direction, and it will still give us a tree of the wrong topology. So that means there's these positive volume regions, so generic regions of parameter space, such that these mixtures are going to give us a tree of the wrong topology under this mixture model. So I think that's an interesting thing to keep in mind because, again, most of the time when we are looking at data, we're not exactly on one of these topologies, on one of these subvarieties. So we're somewhere in this outer space. Okay, so this, as I say, this is just meant to kind of get people interested in the subject. So, well, there's lots and lots of questions. So, well, what happens with 4 states, and what happens with kind of random branch lengths? So branch lengths that we would kind of expect. Well, simple H description in the star polytope, that's maybe a bit of a technical question, but this is, I think, a quite important question that is really relatively uninvestigated. So when is it that 2 trees kind of generate similar site pattern frequencies? And that's, there's a lot of work to be done there, and that's quite important. So when is it that, if you have a certain amount of error, you're on one tree, and you have a certain amount of error, when is it that you're going to pop over to the other subvariety? So when are you going to get the wrong topology just by phylogenetic error? Well, what does model misspecification look like? That's probably going to be a doozy. Okay, what is the likelihood surface for a single tree? I mean, this is one of the most fundamental problems, but we still don't really know what that's going to look like. It doesn't appear that we know the complexity, the time complexity for maximum likelihood on a single topology. So is it polynomial or is it NP complete? So it's known, of course, that the whole ML problem is NP complete, but this still is not known. Generally, what's going on in geometry? So this is my to-do. So I think I'm going to organize this geometry website. So what do we know and what would we like to know, essentially? So if you're interested in this, let me know, and I'll send you the link when it goes up. So a lot of this work with the convex hulls and whatnot was done with Mike, of course, and Hutchinson, who's at Berkeley. And I was funded by the Alan Wilson Center, but now I'm funded by the Miller Institute. So if you come by Berkeley, let me know, and we can power up. Thanks.
So isn't it sort of unfair? I mean, to mix things in two-state model just because there aren't enough parameters. I mean, you get sort of A plus B equals C. We C, and you want to reconstruct A plus B.
Yeah, you might be right. Although there's more room to move if you have more parameters. I mean, it's open. So yeah, if it does, I mean, I guess I'd be surprised if it didn't happen on the 4-state model.
I'd be surprised if you did happen, right?
Okay. Well, we can have a wager.
Yeah, have that.
Okay, I think maybe we should begin the switch, if you don't mind. Thank you very much, Eric.